series. So let's just review a little bit about what it means for it to be geometric and then the sums. So if something is geometric, it means it has a common ratio. What does that mean? That means if you divide successive terms, you'll always get the same number. So a very easy, let's start with something kind of like a trivial one. Then we'll apply the formula, kind of see how they work, and then we'll go into these more interesting cases. So if we were doubling, 2, 4, 8, 16, 32. If I divide any two successive numbers, 4 divided by 2, 8 divided by 4, 16 divided by 8, 32 divided by 16, we always get the same thing, and that's our common ratio. We have a common ratio in this case of 2. Okay, so now if all we had in between these numbers were commas, we would have what we would call a geometric sequence, because it's just a list of numbers with that property. Now what we're moving on to today are series, which means we're actually adding up these terms. So we've got a series that's doubling, and we have two formulas that go along with this. They're actually the same formula, they're just in two different instances. And we have sum of a finite geometric series, and this is from the second page. And these formulas you're going to want to know. We use them a lot in this section, and we'll use them for some proofs later in this section. So to find the sum, let's say that this is a finite geometric series. So if we have a finite geometric series, that means there is a countable number of terms. We know how many terms there are. So to sum up the first n terms, it's the first term, which a lot of times will be denoted a sub 1 or a, times 1 minus the common ratio to the n over 1 minus r. So 3 things you need in order to determine a sum of a finite geometric series. You need to know the first term, the common ratio, which is what r is, and the number of terms. So for our series here, let's assume this is finite geometric, and let's say we just want to know what the sum of the first 10 terms are. Now, one option is to write out the first 10 terms and add them up. That's fine. That will work. But imagine if it was n equals 100, we don't want to add up the first 100 terms. So let's make it 100. So if we wanted to sum up the first 100 terms of our series, S sub 100, it'd be the first term, 2, times 1 minus our common ratio, which is 2, to the number of terms. So we're doing 100 terms, all over 1 minus the common ratio. That is something we can very quickly put in the calculator to get the sum of. So let's do that. 2 times 1 minus 2 raised to the, and I think you'll agree this is much quicker than finding the first 100 terms and adding those up. So we get 2 points. This is in scientific notation. It is a huge number. If you can imagine doubling 100 times, it's quite a large number. 2.535312 times 10 to the 30. Okay. So this is for our finite geometric series. To do the sum, you need 3 things. First term, common ratio, and number of terms. The other thing that you encountered in 8.2 was infinite geometric series. Okay, now, this is a really cool thing that happens with infinite geometric series, but there is a condition that must be met. For example, if we think about our series up here, if I keep adding terms infinitely, my sum is going to be infinite because I just keep adding larger and larger numbers. So we need a geometric series whose terms get smaller and go to 0. So the infinite geometric series, the sum only exists if the absolute value of r is less than 1. Or we could write it as r has to be in between -1 and 1. So this formula will work for what we call alternating series too, which is when each term swaps signs, so positive, negative, positive, negative. We'll talk more about alternating series next week, but I just want you to know that if we have an alternating geometric series, it still works in both formulas. Now, the formula for the sum of an infinite geometric series might be one of the easiest formulas we see all semester. It's very similar to this formula, but here's what's cool. If r is less than 1, well, then the limit as n goes to infinity of r to the n equals 0. So basically, this part here becomes 0, and that turns the finite formula into the infinite formula. Well, if that's 0, this is just 1 minus 0, so the top is literally just the first term over 1 minus r. All right. Now, if we wanted to see what this looked like, let's do something where the numbers are cut in half every time. So maybe we're trying to sum up the term, let's see, 20 plus 10 plus 5 plus 5 halves plus 5 fourths. And then this is an infinite series. So plus dot, dot, dot. Well, to do the sum, we need the first term, which is 20. And we need the common ratio. And it has to be in between -1 and 1, which if we divide any successive terms here, right, 10 over 20, well, that's the same as 5 over 10. We can do this with any of these. They all come out to be 1/2. So that is our common ratio. So 20 over 1 minus 1/2. This one we can do by hand. 20 over 1/2. 20 divided by 1/2 is 40, and that's our sum. So this infinite geometric series is able to be summed up because the terms eventually go to 0. So those are really the two instances we're looking at in this section. And these are going to be the two formulas we're going to be employing today. And I'm just going to show you a couple of real world scenarios where they show up. So this is going to be a present value problem. So geometric series show up a lot in finance. So for those of you guys who maybe go on and with any kind of financial math, actuarial math, things of that nature, you will see geometric series quite a bit. So I'm going to talk a little bit about present value. It's okay if you haven't heard it before. We're just going to talk about it in a very basic sense. So present value is the present value of money that will have a future value. All right. So if you think about what's called the time value of money, $100 now, today, is going to be worth more than $100 a year from now because of the interest that can be earned on it. It'll be worth more a year later. It'll be worth more 30 years later. This is going to be a very familiar looking formula to you guys. B equals P times 1 plus R, sometimes to the T or to the N. Let's use T, that's fine. Where T is in years, if R is an annual interest rate. So our $100 would be here, our interest rate would go here, and however many years goes here. P is kind of like the present value. So it turns out if we solve this for P, so divide by both sides by this, the present value of some amount of money in the future, this is B, sometimes you'll hear this called future value. And sometimes you'll hear this called present value, so PV. But here's, again, you don't need to know everything about this. Let's clean those up a little bit. Here's what we need to know. This formula you guys have seen before in algebra. We know that this computes the balance after T years of some principal amount. So what does this do? That reverses it. This says, okay, if I want to have a certain amount some number of years from now, here's what I need to have now. All right. Now here's an example. This sheet is going to give us an example where this is actually relevant in every day. For instance, the lotto. So with the lottery, you know, there's always, they say the lotto has $100 million jackpot or something, because when somebody wins, they're going to get paid an annuity that eventually pays them out in that amount. Now, you probably also have heard, if you decide to take the lump sum, you get significantly less. The reason you get less is because you get what's called the present value of that annuity. So let's talk through this example, and then we'll see how a geometric series applies. Let's, you know, to make the numbers kind of easy, let's say somebody wins $30 million jackpot, right? There are different ways that lottos pay out, but we're going to assume that this lotto pays $1 million annually for 30 years, hence the $30 million jackpot. So what you would hear on the radio is Bob won the $30 million jackpot. What that means is Bob's going to get, if he chooses, $1 million annually for 30 years. That is not what he'll get if he takes the lump sum. The lump sum is the present value of those 30 payments. Okay? So what we need to do is we need to come up with the present value of those 30 payments. Now, the winner is going to get $1 million right away. And instead of writing out $1 million, let's just write it as 1, just to make it a little bit easier. So the present value of $1 million now is $1 million because there's no opportunity to earn interest on it. Well, he's also going to get $1 million a year from now. But that $1 million is going to have 1 year to accrue interest. And we're going to do this at 5%. So 1 plus 0.05 to the first. That's the present value of $1 million a year from now. Now we can see that the 1 plus 0.05 is 1.05. So that's going to be the 1 plus R for all of these. So this is what he gets this payment right now. This is 1 year later. He's going to get another one that is after 2 years. Well, the present value of that is $1 million, but then it gets divided by the 1.05 twice because it had 2 years to accrue interest. And this keeps going. So 1.05 to the third. And you can kind of start, and here's the coolest thing about, that I think is the coolest thing about geometric sequences and series. It all comes down to identifying patterns. Notice what's happening in this pattern. The exponent of the denominator just keeps going up 1 each time. So if we can think about his last payment, we don't need to write out all the other ones. We know it's going to be 1.05, and now we have to be a little careful. First thought might be 30. But remember, he got a payment right away. So this is kind of like if t were equal to 0. So year 30, his 30th payment is going to be to the 29th power, because that's going to make for 30 total payments, right? Because if we count from 0 up to 29, that's 30 numbers. Just like counting from 1 to 30 is 30 numbers. So what we're doing is we're taking the present value of each of the winner's payments and adding them up, because that gives us the present value now. The present value is the sum that is of these numbers. Remember, the nominal rate, but the not rate, excuse me, the nominal amount of the award is $30 million. Okay. Well, here's what's really cool about this. Whenever you see that, whenever you see an exponent increasing or even decreasing, that's a hint that you might have a geometric series on your hands. Because look at what's happening to get to each next number. We're dividing by 1.05 one more time. In other words, if I take successive terms, if I take these two terms, 1 over 1.05 squared, divide that by 1 over 1.05, you divide by a fraction, you flip and multiply. And we get 1.05 over 1.05 squared, which reduces to 1 over 1.05. What this is our common ratio. We have a geometric series, so we don't have to calculate all 30 numbers and add them up to get this present value. We can use that formula for the sum of a present value. Remember, there were 3 things we needed. We needed the common ratio, 1 over 1.05. That's some decimal, but we'll let the calculator take care of it. We need the first term, which we know is 1, and the number of terms, which we know is 30. So the sum of these 30 terms is the first term times 1 minus our common ratio. And one of the things I'll do a lot today, you'll notice, is I'll put things in exactly because the calculator can handle it. And it helps me avoid roundup. Remember, we're talking about money here. Everybody cares about money. So we don't want to be off by a few dollars, because that means somebody's out a few dollars. Number of terms goes here. There's 30 terms. It doesn't go off of this number. It goes off of the total number of terms. And that's why we're using 30, because there are 30 terms in this series, okay? You'll get some practice with that in the homework. And then divided by 1 minus 1 over 1.05. All right, so what we were about to calculate is the amount you would get today if you decided to take the lump sum. Let's see, let's bring over our calculator. We don't need to put in the 1 for this. So 1 minus, and I'm going to put it in exactly how I have it written. To the 30th. Divided by 1 minus our common ratio. All right. This is our number. 16.141073. I'm going to keep all the decimals because we're in millions. So the present value of that $30 million jackpot, what the lotto has to have on hand so that they can say that they have a $30 million jackpot, is $16,141,073.58. All right, so just a little bit more than half. So that would be the number that you would get if you said, okay, I want to take the present value. Now, you actually wouldn't get that. This isn't part of the geometric series. It's just some fun stuff. you're going to get hit at a 37% tax rate on that money, 24% of which is taken right away. So let's see, if we took off the 24%, that would leave us with 76. So don't get me wrong, still a very nice payday, right? But what you would receive from the lottery is $12,267,215.92. And you would still owe the additional 13% tax on that at the end of the year to the IRS. All right, so that's just, that I think is just some interesting stuff about the lotto. But the reason I like this problem is we've all heard the lotto jackpots. We've all heard about, hey, if you take the lump sum, you don't get as much. There's a lot of theories as to whether it's better to take the lump sum or the payments. You can cross that bridge when you're in that position, right? But what I really like about this one is it shows the time value of money, right? The lotto only needs a little bit more than half of what the stated jackpot is in order to be able to cover. And then what they do is they pay an annuity that pays in annual installments. Now, for those of you guys who do go on, it depends on, for which direction you're heading. A lot of times this present value formula will already be solved in this form. Not in this form, excuse me. Yes, actually, will already be solved in this form and called the present value formula. So a lot of the financial formulas, we're going to look at another one here in a couple minutes. They're usually already in the solved form. The reason I'm going through that part is I want you to see where the geometric series is within these formulas that get used all the time in financial mathematics. The TI calculators can do, some of them have financial calculators that automatically calculate present value, just knowing the payment, the rate, and the number of years or months or whichever you're using. So what we're doing today is we're looking at how the geometric series actually plays into this. To ask, like I said, I think this is a cool one. The other one I picked out is from the book. I'm going to go through some of the parts with you. If you don't, I'll throw the link to the section we're on. If you want to pull up the book on your computer. And we are going to go to the exercises. And I'm going to go through this problem only because it does take a little bit of algebra. But I want you to see. So we're going to go to number 9 in the exercises. And I'm going to work through and put this in a form that we can use it to answer some questions. And I want you to see, this is, doing these making these formulas is not something I'm going to ask you guys to do. Okay, so I don't want you to worry about that. This is more, I want you to see where they come from, and I want you to see how the geometric series plays into what we're doing. Okay, so the next part is going to talk about mortgages or auto loans. So anytime you take out a mortgage, you borrow something called the principal, and it gets paid off at some fixed percent. And what you do is you make monthly payments. We'll call those M. All right. So what happens in this, and some of you guys have probably already experienced this, whether you bought a house, bought a car, right? You have a fixed payment that you pay every month, and the interest you pay is based on the principal at the end of the month. So as your principal goes down, the amount of interest you pay goes down. So we're gonna walk through this. I'm gonna set up the formula. I'm gonna show you a little bit of the algebra behind it, because I really want you to see where the geometric series comes in on this one. And then once we have the formula, let's have you guys solve a couple problems with it. All right. So basically, we're at some interest rate, R%. Okay. And so what happens is that R gets broken up over our 12 months. And so each month, you only pay 1/12 of the total interest rate. Now, what happens each month is you have some monthly payment, and then you pay off that payment. Some of it goes to interest, the rest goes to principal. So this here, this M minus R over 12 times P, R over 12 times P is the amount we're paying in interest. So our monthly payment minus the interest is what goes towards the principal. All right. So I'm going to write some of this down so you guys can follow along. So when they say, so what would the book's calling P1, that's our payment. That's our payment after 1 month. Okay. So what's going to happen is we're going to have some principal amount, and that is going to be decreased by our monthly payment less the amount that we paid in interest. Okay? This is the amount we paid in interest. The rest of our monthly payment went towards the principal. So our principal after 1 month is our initial amount. This is our initial amount, the initial loan amount. Let's write that down. P equals our initial principal. So that's our if we borrow $100,000, that's the 100,000. So that's our initial principal. M is our monthly payment. Okay, that's what comes on our car bill, mortgage statement. It's the same every month. R over 12 is our monthly interest rate. And what happens is we're going to start to see a pattern emerge. Now, what we're going to do is we're going to rewrite this. And this is, again, not something I expect you to know or memorize or anything like that. I'm doing this because I want you to see where the pattern comes from. So I'm going to distribute this negative. So P minus M, that becomes plus R over 12 times P. And I'm going to group those terms with the P in it. So P plus R over 12 times P minus M. That allows me to factor a P out. And that's going to leave me, I'm going to write it the same as the book. I think myself, I like writing it the other way. I want it to match up with the book. If I factor the P out of those two terms, I get something that looks like this. Okay. So again, it's based off of this way of thinking, the principal, minus the amount of our monthly payment that goes towards the principal. This is our monthly payment minus our interest. Then, here's what's really cool about this. This is the pattern thing. The same thing is going to happen the second month. I'm going to not go through this. It's basically going to work out the same way. So the principal left after 2 payments is going to be the principal after 1 payment minus the amount of the mortgage that goes towards the principal, which is our monthly payment, less the amount we pay in interest, which again now is based on the principal after 1 payment. That's what P1 is. So P1 is the principal after 1 payment. Because our principal's going, right? We made a payment. Some of that went towards principal. So that's the That's going down. And that's going to keep going, for P2, P3, so on and so forth. So P2 is our principal after 2 payments. The same algebra is going to apply. We could do the exact same algebra, which would give us 1 plus r over 12 times P1 minus m. Well, what's P1 equal to? It's equal to this, right? So we're going to take this in and sub it in to P1. So what does that do? And this is where the algebra, it can get a little, I don't want to say complicated, a little messy just because my handwriting's messy, really. But it's pretty cool the way things end up working out. So basically, I'm just subbing this in for P1. So that's our sub in for P1, and then we got this minus m hanging out. Okay, now I'm going to distribute this to these 2 terms. If I distribute to that term, I have 2 of the 1 plus r over 12s to the terms. R over 12 squared times p, and then I'm going to have one of them times the m. So I have minus m times 1 plus r over 12. And then we have this minus m hanging out at the end. All right. Now, this pattern is going to continue. So what happens when you do P3? So without doing all the algebra, it's going to be the same thing. What you would do is P3 is P2, P3 equals 1 plus r over 12 P2 minus m. So you literally do the exact same algebra that we just did. And what that ends up looking like is 1 plus, you would sub in P2, you take this line here and sub it in for your P2. 1 plus r over 12 cubed times the principal. And then here's where it really gets interesting. You'd have m times 1 plus r over 12 squared minus m times 1 plus r over 12 minus m. And here's where the pattern really starts to emerge. Remember what we said before about exponents. Notice the only difference, squared to the first, we could think of this as 1 plus r over 12 to the 0. This part here with the m's is actually a geometric series. Let's take that out of there because I don't want it to look confusing later. So we have a geometric series here, and then we have an exponential piece here. So we can generalize this. We have to go over to a new slide for the nth term. So p sub n equals 1 plus r over 12 to the n times our initial principal minus, and now what I'm going to do is I'm going to factor out the m. So let me go back over. I'm going to factor out a negative m out of these 3 terms. And let me do this in 2 steps to make it real obvious what's happening here. So if I factor out that m, I'm going to have 1 plus r over 12. Now notice, if this is to the nth power, for instance, this was to the 3rd, the first one was to the 2nd, this one would be to the n minus 1. And we would have all the way down to 1 plus r over 12, and then plus 1. And there are pluses in here because I factored out a negative m. Right there is our geometric series. And this is how a geometric series is going to play into this. Now remember what we're doing. P sub n is the amount of principal left after n payments. So this will calculate it. And what we need to know is the interest rate, the number of months, because we're doing monthly payments, so n is number of months. We need to know the initial principal and our monthly payment. We know those things, we can calculate this. Well, this is a mess. Let's clean this up. This is a geometric series with a common ratio of 1 plus r over 12. And it is finite. It's a geometric series. It has n terms. Let's see. N terms. And its first term is 1. So here's a little bit cleaner way to, it's not going to be the prettiest thing you've ever seen, but it's going to be a lot easier to work with from a mathematical standpoint. Minus m. And now we're going to do our geometric series. The first term is 1 times 1 minus our common ratio, which is 1 plus r over 12 to the n, over 1 minus 1 plus r over 12. This is that same formula we used last time. We can make this a little bit easier to work with. If I distribute this negative, I'm going to end up with 1 minus r over 12. Remember what happens when we divide by a fraction? We can multiply by the reciprocal. So what we're going to have is 1 plus r over 12 to the n times p minus, now we're just going to multiply by 12 over r, so 12m over r. That gets rid of that whole denominator. Because this is just 1, I'm not going to rewrite it. So 1 minus 1 plus r over 12 to the n. Like I said, not the prettiest formula, but very powerful because this will give us the principal after n months. Okay? It's essentially the same formula. Oh, yes. Actually, we can simplify this a little bit more, and I will. Sorry. One more step of simplifying. I can distribute this. So let's talk about what happens here. And this simplifying is definitely worth it. It makes this thing a little bit even easier to deal with. So minus 12m over r times 1 doesn't change it at all. And then we'll distribute it to here. A negative times a negative becomes positive. 12m over r times 1 plus r over 12 to the n. Now here's why this is useful. We have a common factor on those two terms. So I can bring those together and I can factor out the 1 plus r over 12 to the n, and that's going to get multiplied by p plus 12m over r, and then minus this 12m over r hanging out at the end, this guy here. All right, again, not a formula I want you to memorize at all, guys. Again, this is to show you a real world example of a geometric series that is used all the time. Again, what will this do? This will give us our principal after any number of months. Now here they changed the n for 12t to make it in terms of years. I'm just going to leave it this way and do it in terms of months. Let me show you how this works. All right, so we're going to look at G. Make this is part G here. Let's make that a little bit bigger. All right, suppose that we have a $1,000 balance and we're going to get charged 20% interest and we're going to pay $25 a month. And we want to know how long it's going to take us to pay off the $1,000 charge and how much we'll have paid on this $1,000 charge. Well, then what we're trying to solve for is N. Okay, a couple different ways you can do that. Number one, you can solve for N from the beginning, or you can wait until the end to solve for N. But here's, let's do this. I need a little bit more space. All right, so we've got our formula, P sub N equals P minus 12M over R times 1 plus R over 12. Again, I'm just going to do it in number of months. I'm not going to worry about changing it to years. We can convert at the end. This is our formula. Now, if we want to pay off a whole balance, we want the principal after all our payments to be 0. So what we do is we set this to 0 and we solve this guy for N. So, and again, if we're doing it for a specific problem, well, we could plug in all the numbers now, right? We know that for G, P equals 1,000. R equals, remember for percents, you have to convert them to a decimal, 0.2. And M, our monthly payment, is going to be 25. So we know all these numbers. We know everything except for N. I just want you to see what this thing looks like solved for N. So first thing you'll do is you'll subtract this guy over. So minus 12M over R equals P minus 12M over R times 1 plus R over 12 to the N. And then to solve for N, we'll need to divide by this guy on both sides, P minus 12M over R, P minus 12M, oops, too far, over R. And so once we do that, notice what we got left. So minus 12M, let's write it this way to give it a little bit more room, over R, P minus 12M over R. And we have something left where we have to get N out of an exponent. So this is going to use logarithms. You can use the common log or natural log. I like using natural log. So I take ln of both sides. That allows me to put that N out front. So I have N times natural log of 1 plus R over 12 on the right-hand side. So I divide by 1 plus R over 12. And I get that over ln of 1 plus R over 12. So this is tell us how long it's going to take to pay this off. I know it's not pretty, but we have calculators to do this. So let's see how long it's going to take us and how much we actually pay in interest. So N equals natural log of negative 12 times M is 25 divided by 0.2, our interest rate, over our principal amount, which is 1,000, minus 12, and again, times 25 divided by 0.2. And then our denominator ln of 1 plus 0.2 divided by 12. Okay. Like I said, I think it's best to put these in the calculator all at once. Don't even need that for the numerator. The reason being, it avoids any round off error. It's easier to fix mistakes. 12 times 25 divided by 0.2. There's our numerator divided by the denominator. Does need to go in this denominator here. I guess we got a couple denominators. 1,000 minus 12 times 25 divided by 0.2. Okay. Now that is our first natural log divided by natural log of, this one isn't quite as bad, 1 plus 0.2 divided by 12. So we find out it's going to take about 66.46 months. So we'll probably need to round that up because after 66 months, we won't have quite paid off enough. So maybe, so we have 66 and a half months. You can convert that into years by dividing by 12. So if you want to know how many years that's going to take, it's about 5.5 years. But if we do this for $25 a month for 6.5 months, so let's go back to where we were. Here's how much we'll pay total. So the amount we're going to pay in interest on that $1,000 credit card balance and I misspelled the heck out of that word. Excuse me. Let's try that again. Interest is $661.61. So again, take a deep breath. I know there was a lot of stuff going on. What I want you to take from this are two things. Number one, how a geometric series plays into a lot of our financial formulas. And two, how once we have the formula, all we do is plug in our knowns and solve for our unknown. Questions at this point? Now, we could do something really similar. We could solve for M if we wanted to do monthly payments. Excuse me, if we wanted to solve for the payments. So we've got to, here, let's circle that so you guys can, because you guys are going to use these to try a couple of these problems. Right there, that will solve for how long it would take to pay something off. This formula here, now this is in years, so I'll rewrite it in our notation where we're doing it in months, and it's up to you, whichever you like. I mean, they both work fine. I just like sticking with months on this one. If we had solved for M instead of N, we would have gotten R times P times 1 plus R over 12 to the N. Again, I'm doing N in months, over 12 times 1 plus R over 12 to the N minus 1. So in this case, you'll be trying to solve for the monthly payment. All right. So